You've downloaded hundreds of gigabytes of these .gguf files. You run them with Ollama, Llama, C++, whatever. But what's actually inside them? It's not just weights dumped into a file. There's a whole structure. There's metadata, quantization info, naming conventions, and architectural details, all packed into one file. And so in this video, we're going to look under the hood. We're going to walk through the GGUF spec. I'll show you what each part means, how quantization actually works, and how to inspect your own model files. GGUF stands for GGML Unified Format. It is the successor to GGML, GGMF, and GGJT. This is the fourth iteration of a format designed specifically for running large language models more efficiently. And if you're wondering what the GG stands for, it's for this guy, Georgy Gerganov, who invented Llama C++, Whisper C++, and a bunch of other things. Here's his website. He's a genius. So a couple of the things that sets GGUF aside from other formats. One is obviously the single file deployment. The other one is that it's language agnostic. GGUF files can be read and written in C or Python or JavaScript or Rust or any language. But the key thing is mmap compatibility. So it's memory map compatibility. That means loading only the tensors you actually need into RAM. That means that a 70 gigabyte model might only use 20 gigabytes of your actual RAM. The operating system loads only the tensors you need when you need them. And if you compare that to something like raw PyTorch weights, which loads everything all at once, whether you need it or not, it gives GGUF a huge advantage. This is the file structure of a GGUF file. It has 5 sections laid out in order from start to finish. First, the header. It's only 20 bytes. It contains the magic number, the version number, the tensor count, and the metadata key value pair count. After the header, we have the meta key value pairs. Now, this is where all the intelligence lives. Architecture type, layer counts, vocabulary size, author, description, hundreds and hundreds of fields, all structured with dot notation keys, very similar to JSON. Then we have the tensor info. This is each layer's name, dimension, data type, and so forth. This tells the loader exactly where to find each piece of the model. There's a fourth section called padding or offset, where the files are aligned to a boundary. And then fifth and last is the actual tensor data, the weights, biases, and embeddings. This is where most of the file size comes from. So to get a look at how we can access that information, I'm opening up my path to my model here. I'm assigning the first 4 bytes to magic, the next 4 bytes to version, the next 8 bytes to tensor count, and then the next 8 bytes to KV count. So we get our magic, our version, our tensor, and the number of metadata pairs that we have. And if I run that guy, we can see we get GGUF, we get version 3, 733 tensors in this particular model, and 54 metadata pairs. This is exactly how Ollama or llama.cpp or whatever LLM runner you're using can look at a model, find out what it's all about before it ever loads all those weights. So this is the part that matters most for local AI, quantization. So quantization is the reduction of the precision of a model's weights. So full precision is going to be called FP32, which uses 4 bytes per number in the weights. And then quantized version use fractions of bytes. GGUF supports 15 quantization types, and they are FP, or full precision, 32, which is the 4 bytes per weight that I just mentioned. This is perfect quality. And for a 7 billion parameter model, this is going to be about 14 gigabytes. Then we get FP16, which is 2 bytes. So it's going to be half the size at 7 gigabytes. Then we get to Q80, which is 0.88 bytes. It's going to end up at 4.3 gigabytes for the same model. Then we get Q50 and 1, which is around half a byte. This is good quality. It's going to end up between 2.8 and 3.1 gigabytes. Then we have Q40, which is 0.42 bytes per weight. This is still good quality. It's 2.1 gigabytes for the same 7 billion parameter model. Then we get to like Q4K M, which is also 0.42 bytes, the same as Q40. But this K is called K-quants, or it stands for K-quants, which is a quantization scheme that like allocates bits more efficiently than the Q40 method. You're still going to get about 2.1 gigabytes, but technically it should be smarter, I guess. Then we get to Q3KM, which is going to be 0.33 bytes. We get to Q2K, which is going to be 0.25 bytes, and we're down to 1.2 gigabytes. Now, the Q4KM and Q3KM that I mentioned, you can also have S or an XS or an L or something like that there. And that is a little bit of a deeper dive, but it basically means they prioritize certain weights over other weights. So you get kind of a scale of bullshit there that you'll just have to look up. I don't know. GGUF files are supposed to follow a naming convention that tells you everything about the model at a glance. Now, it's not always perfectly followed and it's not super strict, but the basic structure of a GGUF file name should be base name, size label, fine tune, version, encoding, type, and shard. So let's look at an example. Here, our base name is Grok. Our size label is 100 billion parameters. Our version is 1.0. And our encoding, or quantization, is Q40. Okay, let's try another example. Here, our base model is Quen 3.6. Our size label is 35 billion. We have a fine tuning of A3B. Then we have a certain kind of fuckery that a lot of companies or organizations like to do, and this stands for unsloth dynamic. They want you to know they made this guy. And then we have our encoding or quantization of Q4 with a K-quant of XL. So, what do you take away from this? Well, first, GGUF is the format. If you're doing local AI, you're using GGUF. Every tool, Ollama, llama.cpp, V, LLM, MLX, everyone's using it. Second, quantization matters. Q4 KM is probably your default. Go higher to Q80 if quality matters and you have the space. And then you can always go lower to Q3K or Q2K if you're tight on disk space. Third, you can inspect any GGUF file you like. The header and metadata are always at the front. No need to load the full model. I'll link the Python script that I shared in the description, just so you have access to that. So I hope you learned something useful about the GGUF file format, or more importantly, the file naming conventions, which can be really crazy. And I hope you can put that to use. I'm Joe Metalone. I make short, practical videos that respect your intelligence and your time. If that's your style, you'll like this channel.